Okay, does that turn up? All right. So 18B, we're in 18B now. All right. All right, so let's review resonance. So some key resonance structures we'll see in this class are stuff like this. All right. So you want to be able to draw resonance structures for benzene rings and when you have heteroatoms, okay? So this is what we call resonance donation into the benzene ring, okay? So you can see here that I can put this electron pair onto this carbon, and this will make this carbon particularly nucleophilic because it has excess of electrons. So it's electron rich, okay? So if we draw this, where is my like what charge is going to appear on the left carbon of the ring? So we have this charge. We have this group right here, right? What's the charge on this oxygen now? Positive, right? So if I have a positive forming, I must have a negative charge elsewhere in the molecule. Where is that going to be? On the carbon without an octet, with more than an octet now. So you can put the lone pair there, and now it's still negative charge. Okay. So when you have certain groups on the benzene ring, it makes the carbon have negative charge. It'll have the structure. Some structures will have negative charge in the ring. Okay. So you can also draw another resonance structure where you put this down here, and then you can see here, you can move the charge over one carbon around the ring. Okay, so you can push the charge into alternating carbon positions, and that tells you when we talk about reactions like these with benzene, that this negative charge will dictate where electrophiles can add onto the benzene ring. Okay, so we're not going to touch the oxygen here. We're going to keep it the same here. Okay. But now, this is going to become a double bond, and then negative charge there. All right. So there's one more resonance structure we can draw. Where will the negative charge be in this next structure? Oops, I can't write on that side. All right, so in each of these structures, there's still a lone pair. Okay, so where is the double bond? How are the double bonds going to be in this last structure? Or where is the negative charge going to be in this case, in the last resonance structure that we could draw here? Yeah, the carbon right here. Thank you. All right, and then that means this double bond has formed here. So by looking at the structure, we can go back to the left structure and write the arrows. So someone help me write these arrows. This one's going to come out on this carbon. So where is this lone pair? Where's this lone pair on the bottom going to go? Where is this one going to go right here? If we look at the structure on the right, so where should we point? Anyone? So I'm going to draw an arrow from here, pointing to where? if I'm going from left to right. Look at the left structure and look at the right structure. How do I get that bottom double bond? All right, move this one. Am I going to move it to the right or the left? Yeah, there you go, right there, right? There you go. So you see here we have 3 positions where the negative charge is forming. Okay? So if you actually put this, this is called phenol. So if you put phenol in the presence of a good electrophile like bromine or chlorine, this is you're going to see that products will be attached here. Okay? So these 3 positions, these are called nucleophilic sites. Okay? So you might think, oh, oxygen's a nucleophile. But no, when oxygen is attached to a benzene ring, it makes the carbon the better nucleophile. And so we'll see this type of reaction based on the resin structures that are drawn here. Okay? So now, but there's one more structure we can draw. So let's draw the last resin structure. This is where we restore the benzene ring, and then we pretty much get to the same structure we started with. Okay? So this one, we're going to draw an arrow here and push these back out, and we get benzene here. Oh, notice I actually drew it incorrectly. Sorry, just redraw that. Okay. Sorry, I drew the arrows in the wrong place. Where should my double bond go instead? Not to the left, right? To the right. So right here. There you go. All right, so out of these resin structures, which one's the best? Well, which one is like the most stable? The last one or so this last one or the first one, right? But they're the same thing, so they're it's just the double bonds are alternating, right? So they're the same thing. So this one will be the most stable. So in this class, you won't have to recognize which is the most stable, but you should be able to recognize which resonance form is responsible for, say, reactivity. And we'll go into that later throughout this semester. Okay? All right. Are we comfortable with resonance? Should we do another one? Okay. Does anyone need this page still? Are we okay? All right. So, let's see. What's a good one here? All right. All right. So later we'll learn that if you treat a ketone with a suitable base, okay, you can generate a reactive intermediate that is resonance stabilized, okay? So remember, reactive intermediates, reactions occur if a species along the reaction is stabilized in some way. That makes a reaction occur. If that species is too unstable, too high in energy, it's more unfeasible to occur, okay? So this hydrogen, remember when we talked about acidities, this hydrogen is acidic, okay? Acidic, all right? So compared to like this group right here, if we compare it to this, so compared to CH4, okay? So we have this hydrogen right here. So what's the difference between these two hydrogens that I've circled here? One's attached to carbon, but they're actually both attached to carbon, right? But what is that carbon also attached to if we consider the first structure? Yeah, carbonyl carbon. Well, we know oxygen, right? Very happy to accept electrons, so it can actually make something more acidic. So let's demonstrate here. So I'm going to use my base to remove this hydrogen. Okay, so now this, it will come out here. Now this carbon has two hydrogens and a negative charge, right? So it's missing a hydrogen. It has a lone pair, so it has an excess of electrons. Okay? Now, if I compared that with this conjugate base, so say I use a base and removed this hydrogen, okay? I get a carbon atom or a carbon ion that's not very stable. All right? So one of these is more stable than the other. Which one is more stable? Which conjugate base or which anion here is more stable? Is it the one with the carbonyl or the one with just a carbon atom? All right, let's think of it this way. So the pKa of this is about 50. Okay. And we want to take a guess, what's the pKa of this acetone right here? All right, I'll tell you. Anyone have a guess? Is it going to be more than 50 or less, do you think? Less. So this is actually more than half times as less. So it's like 10 to the power of 25 times more acidic. Okay? And there's a reason why. If we look at the conjugate base, this charge, so the negative charge here is localized. That means it's stuck, not stabilized. Okay? But what can we do with this charge right here? What can we do right here to stabilize it? Any ideas? Oh, yeah. Yeah, so it can participate in what? Starts with an R, resonance, yes. So this will stabilize this group because we can draw a resonance form. And now where's the negative charge going to go? Yeah, so the more favorable or more able to handle a negative charge, oxygen, right? Okay? Like this. All right. And this has a special name. So this is called an enolate. So remember on those course objectives, it said enolate type reactions. This is an enolate. Okay. Why is it called enolate? It has an oxygen negative charge. So remember, anything with oxygen, the suffix is ate, A-T-E. All right. That's that prefix right here. So this stands for the O minus. Okay? Ene, what does ene sound like? What functional group does ene sound like? E-N-E. Yeah, I heard that. Alkene. Okay, so this is an alkene. Well, there's oxygen here. Oh, it's negatively charged. It probably wants to get rid of that negative charge. So this can actually be used. So this form of the molecule is actually a great nucleophile. So we'll learn about why this is a nucleophile, but you wouldn't expect this to be a nucleophile if you didn't consider resonance. So that's why from now on, we have to think about resonance and how does it change a molecule's behavior. Does it make it more acidic, less reactive, or can we create an intermediate and use that to kind of build upon what we learned about nucleophiles and electrophiles and use that to do interesting chemistry, okay? So that's what I wanted to get my point across. So we have to realize, remember pKa and resonance, two of the most important concepts we learned in 18A. Okay. Are there any questions about this scheme here? No? Okay. All right. So I'll tell you right now that there's other compounds that can do this, okay? So we looked at this compound, right? So this compound, we can also do this if we have an aldehyde. So you have an aldehyde, add a base, you can get the aldehyde version of an enolate. Okay, that's also possible. Okay, you can have two carbonyl groups together, separated by a lone carbon atom. And if you add a base here, you can also do this type of resonance structure. But the double bond won't actually be on the outside. It'll be where? Yeah, you're right. Between. That's more acidic if you're flanked by two carbonyl groups, like this. So we're going to see these types of chemistry in this semester. So these are the most important types I want to get across, okay? And so so it doesn't matter what kind of carbonyl group you have, really, as long as one of them has a carbon atom, okay? So here's some more examples of things that do this. So the other common one we'll see is if you have an ester. So we have RO here, okay? This, if you add a suitable base, okay, the base actually matters here. So we'll just keep it like that. This can also do this type of chemistry, okay? So the ester group is left unchanged, but here, sorry, I made a mistake. Let's erase that. I should have put a double bond there. Okay, so you do see this kind of predictability here in the chemistry of the carbonyl. So you have a ketone, aldehyde, all right? So this is a ketone, aldehyde, ester, and this is called a 1,3 dicarbonyl. All right. So this molecule is actually called not acetoacetate, but 1,3. What's it? Dipropanone? Yeah. 1, 2, 3, 4. 2, 4. Oh, well, there's a way to name this one, but don't worry too much about that one yet. Okay, this one. All right. Okay, so those are just a preview of the resin structures we'll kind of see here, okay? All right, so in terms of which one's more acidic, we won't worry about that yet, okay? We'll get to that point later on in the semester. All right. All right. So we're going to see that type. So this is how we relate resonance to acidity here, okay? So you're going to see more of this type of chemistry. So be on the lookout. If you see a compound and it's just like a base and the reaction, you're probably going to do something like this first, and we'll have to be able to connect acid-base reactions with different other reaction steps to kind of see how it plays out in the mechanism, okay? So I just want to review acidity here and resonance. All right. Okay. So let's see. Let's do a new page here. Is anyone still writing stuff down? Okay. All right. All right. let's see. Let's do one more for acid base. So we did acid base, and then so let's see how this is important. Okay. So say you have an alkyne. Okay. So what's nice about alkynes here, as opposed to alkenes and alkanes, they can be deprotonated, okay? So why do we add acids and bases in the first place? Well, it helps us generate good molecules to react very easily, okay? So let's say we have a base here. So our base, let's just make it an amide. So a very strong base. You have a negative charge on the nitrogen, okay? All right, so which hydrogen here is more acidic? HA, HB, or HC? All right, this is going to segue into what we'll talk on Thursday, which is alkynes. We'll start talking more about alkynes. So this is kind of a great way to lead into that because we have an alkyne right here. So you got to remember, which one actually is more acidic? HC, HB, or HA? All right, her and B and C. Okay. So what I want you to remember is that, so if you have something with an alkane, so a CH hydrogen, like this one. So I think it's inevitable. We'll have to kind of remember the values for alkanes, okay? So this pKa is about 50. Does anyone remember, well, okay. So HA, so this falls under HA and H. And which other hydrogen here is kind of an alkane type hydrogen? HB or HC? HB. So you may be wondering, well, HB, couldn't HB do resonance? So what if you did this, right? Look at this. You deprotonate HB, you get this negative charge. Isn't it true that you can do resonance here? Right? You could push electrons here and push it on this carbon. Well, but what's the bad thing about pushing it on that carbon? Will carbon necessarily stabilize that charge? Is carbon good at stabilizing a negative charge? All right, where's the negative charge going to be? Right here. So if we did that resin structure, alkenes are not very good at stabilizing negative charge, okay? Because here we have what do we have here? Well, it's still sp, okay? But it's a double bond. So it might not be as stabilized as an alkyne, okay? So this pKa of this hydrogen, HB, it's not going to be as low as an alkyne, but it's not going to be as high as an alkane. So its value is in between 50 and 25, okay? So it's still not the most acidic. The most acidic one is the alkyne hydrogen right here, okay? So say this is an R group right there, all right? So this pKa is roughly 25. So this one is the most acidic. So this hydrogen right here, that's the most acidic. So that's going to be preferentially deprotonated, okay? Because on this carbon right here, okay, if you look at this carbon is not as stabilized as if you had this. So let's pick up this hydrogen and we get this situation where now we have a negative charge here, okay? So that negative charge is more stabilized. Do we remember the trend in acidity for sp3 versus sp2 versus sp? So in terms of this graph here, which a charge on which kind of carbon atom, or which carbon atom here. So we have an sp carbon. All right, which one will have a higher, a more acidic hydrogen? sp2, or sp3? You guys recall? So which one has more spherical character? sp, right? So this is more spherical. This looks like more p orbital like, okay? And then this even looks less p orbital like, okay? So remember, more s character means more acidic, right? And that's because, the electrons are closer to the nucleus in the s orbital. Closer to nucleus in s-like orbital. And when you have an s-like orbital, right, electrons in s orbitals, they're closer to what in the atom? You guys remember? So s orbitals, the shape of s orbitals, right? They're like the shape of the nucleus. So if electrons are closer to the nucleus, are they more stable or less stable? More stable, right? So that's why they're more acidic. So this alkyne is more acidic because it's in an sp orbital, and that has more s character, okay? And then you can actually use this chemistry here to do reactions. So I can take CH3 iodide here and use that to add a methyl group. And so what I can get here is I get an alkyne and I add a methyl group there. Okay? And this is kind of a preview of what we'll talk about in this chapter in alkynes. Okay? So the key takeaway here is acidity of a compound can be manipulated to take advantage of its acid-base properties, and we can use that to do chemistry we've seen before, acid tube type reactions. Okay? All right, that'll be it for today. Okay, you guys? If there's any questions, let me know, and then I'll see you guys on Thursday.